In this lesson, we'll learn about the Pythagoras theorem and the converse of Pythagoras theorem. You have already used the Pythagoras theorem earlier. Now, for the Pythagoras theorem, we need to have a right-angled triangle. Like in this case, it can be used only in a right-angled triangle. So here we have A, B, C, which is a right-angled triangle. So in triangle ABC, angle B equal to 90. So this is the criteria for Pythagoras theorem. One angle should be 90. If that is the case, then we can say that the hypotenuse square. Now, who is the hypotenuse? The side opposite 90 is the hypotenuse. So here in this case, AC is the hypotenuse. The hypotenuse square, that is AC square, will be equal to the sum of the squares of the other sides, AB square plus BC square. This is the result. Now, when it comes to converse of Pythagoras theorem, here again we have a triangle. So a triangle PQR, and in this triangle it is given to you that PR square equal to PQ square plus QR square. If that is the case, then we can say it is a right-angled triangle. Therefore, triangle PQR is right-angled, and since PR must be the hypotenuse, this must be the hypotenuse here. It must be right angle at Q. So angle Q is equal to 90 degrees. So this is the difference between Pythagoras and converse of Pythagoras. In Pythagoras theorem, this is our statement, this is our result, and in converse, the result is the angle is right angle triangle. The sides of a triangle are given below. Determine which of them are right triangles. In case of a right triangle, write the length of the hypotenuse. So here I have three sides. This is say A, then I have B and C. So A equal to 7 centimeter. I have to find the square. A square is 7 square, which is 49. Then B equal to 24 centimeter. B square equal to 24 square, which is equal to 576. And C is 25 centimeter. So C square 25 square equal to 625. And the next step, you take up the two smaller sides. And the smaller size we see is A and B. And find the sum of their squares. Find what is A square plus B square. And then take the third side, which is C square, and find the square of C square. So we substitute. We saw our A square is 49. Our B square is 576. And then you add up, you get 625, and we see the C square is also 625, so it's equal. So now we can say that we know A square plus B square equal to C square. Therefore, by converse of Pythagoras, these are the sides of a right triangle. So these are the sides. Now, who would be the hypotenuse? By now you would have guessed this C square must be the hypotenuse. So the hypotenuse is the longest side, which is equal to C. Let's get on to the next one. This is A, B and C. So A equal to 3 centimeter, B 8 centimeter, C 6 centimeter. Take the two smallest sides and the two smaller sides is A and C. And find the square. Let us find what is A square plus C square. That is 3 square. C is 6 square. So you have 9 plus 36. And adding we get 45. Now let's take up the other the longer side, which was 8 here, and we'll find the square B square, that is 8 square and 64. So here is 64, and we see it is not equal, which means A square plus C square is not equal to B square. Therefore 3 centimeter, 8 centimeter and 6 centimeter are not the sides of an right angle triangle. Of a right triangle. We can say this by Converse of Pythagoras. Now for the next one, we have A equal to 50 centimeter, B equal to 80 centimeter, and C equal to 100 centimeter. Take up the two smallest sides, and the two smallest sides is A and B, and find the sum of the squares. So we have to find A square plus B square. So A square is 50 square, B square 80 square. So that is 2500, 80 square 6400, and this works at 8900. Now the longest side has to be the hypotenuse, right? So C must be the hypotenuse. So we'll find out what is C square. C square is 100 square, which is 10,000. So here we have, now is it equal? It is not equal. So we see that A square plus B square not equal to C square. So 50 centimeter, 80 centimeter, 100 centimeter are not the sides of a right triangle. Now for the fourth sum, A 13 centimeter, B 12 centimeter, C 5 centimeter. Here we pick up the longer side. The longer side is A here. So we find A square. A square is 13 square, which is 169. And we take up the other two, B and C. So we have here B square, and we add them up. B square plus C square. 12 square plus 5 square. 144 plus 25, which is 169. And here was 169, so that's equal. So thus we can say that A square equal to B square plus C square. Therefore 13 centimeter, 12 centimeter and 5 centimeter are the sides of a right triangle. A right angled triangle. If a perpendicular is drawn from the vertex of a right angle of a right triangle to the hypotenuse, so here's a right triangle with 90 degrees at B, and they say we are drawing a perpendicular on the hypotenuse. So I'm drawing a perpendicular on the hypotenuse. I call the perpendicular D. Now if you look at the picture, there are three triangles formed. One is the big triangle, ABC, the original triangle. Now after drawing the perpendicular, I got two more triangles formed. That is triangle ABD and triangle BDC. Now all these three triangles, they said, are similar to one another. That is what this theorem says. So the triangles on both sides of the perpendicular, which are the triangles on the both sides of the perpendicular? It is triangle ABD and BDC are similar to the whole triangle and to each other. It's similar, they say, to this whole triangle. So all these three triangles are similar. But it's important to write the similarity correctly. So we will now learn how to write the similarity of these three triangles correctly. So here's a figure. I'm first going to consider these two triangles similar. The one that I've colored in this color. And yeah, the first one, I'll just write the triangle. It is ABD. And on the other side, I'll take the triangle BDC. Now, one angle is 90. Here, the D in this is 90, the D in this is 90. So I'll write angle D equal to angle D equal to 90. So we've got one angle. Now, again, here is my 90. So you see angle 1 plus angle 2 is equal to 90. This is equation 1. Look up at triangle ABD. In triangle ABD, here I have angle 1 plus angle 3 plus 90 is equal to 180. These are the three angles of that triangle. So I've taken angle 1 plus 3 plus 90 equal to 180. Therefore, angle 1 plus 3 equal to 180 minus 90, and angle 1 plus 3 equal to 90. Equation 2. Now 1 plus 2 is 90 and 1 plus 3 is also 90. So I can say 1 plus 2 equal to 1 plus 3. 1 I take out from both the sides and I get 2 equal to 3. So let's mark that now. This 2 is equal to 3. So I got another pair of angles that are equal. So I have here, this is 3 belongs to this, equal to 2. And in this case, the angle 3 is A and angle 2 here is B. So I'll erase this, and instead of writing 2 equal to 3, I'm going to write angle A equal to B. Therefore, the third angle has to be equal, and the third angle is 1. 1 has to be equal to 4. So, and 1 is B is equal to C. So now the right correspondence for these triangle will be triangle DAB. So I have D here, so I'll have D here, then A here, B here, and B here, and C here. So these triangles will be similar. So let me write that again. So I have triangle DAB similar to triangle DBC, or you could also write triangle ABD similar to BCD. But just remember that if there is A at this point, there should be, now this, there should be B here because A is equal to B. If there is B at this point, there should be C here. I'm referring to this. and then if there is D, it should be D, because both D is 90, the other D also is 90. So if you get a figure like this, you need to always remember that this angle here will be equal to this angle. You don't need to prove it, and this angle will be equal to this. And of course the 90, 90 are there. Now let me try to write the correspondence between the small angle PQS and the large angle PQR. In PQS, the small angle PQS, let me mark the 90. So this S is 90, and in the big one it is Q that is 90. Here this S is 90, and in the big one the Q is 90. Now which is common for both? If you notice, there's S is common for both. Not S, the P is common for both. So I'll write P equal to P because it is common. And then the third angle, we just name it. That is, in this case, it will be Q. Here we have Q. So Q will be equal to the third of this. So that is PQR. The Q is always equal to R. So the correspondence in this will be triangle SPQ similar to triangle QPR. We have taken this small triangle with a large triangle. Now I'm going to take the other small triangle with a large triangle. Here again the same figure, and always I mark this angle will be equal to this. This is a standard, and Q will be equal to R, and then we have the 90, 90. This is 190, this is the other 90. Let me take up the other triangle, that is QSR with the large triangle, and see how to write the similarity. So here we have PQR, which is a large triangle, and the smaller QSR. Always we start with 90. In PQR, who is 90? We saw in PQR, Q is 90. So Q here will come with Q here. No, Q with S, not Q. In the smaller triangle, the S is 90. So we have S here. Here, this is 90 here, and this triangle here 90. Now, which is common for both? You see that R is common for both. So I'm going to write R here, therefore R here. Which is the third angle that is left? I've already written Q, I've written R. Now the third one left is P. So P, and in this case, and look up here at the figure, you know that P is always equal to Q. I put Q. So I got my similarity. Triangle QRP is similar to triangle SRQ. PQR is a triangle right angled at P. So here is a right angle. M is a point on QR. So we have taken point M on QR here, such that PM is perpendicular to QR. Show that PM square equal to QM into MR. So I'm going to take these two triangles, and I know they are similar by the theorem. So let me write the similarity correctly. But before that, in all such cases, we know P should be equal to Q, and here this P should be equal to R. 90, 90. So let's go up and write the similarity. First we'll start with 90, 90. Remember, we are taking in triangle QPM and in triangle RPM. The 90 is M equal to M, which is 90. Then we'll write the next, we'll take the yellow, so that we have Q will be equal to P. If you don't write this correspondence correctly, you will not get your answer. And we have P is equal to R. Therefore, our correspondence, we write MQP is similar to triangle MPR. By the theorem, it was 6.7. Now, now we write the sides. So we have MQ over MP equal to QP over PR equal to MP over MR. Here we require PM square. Now where is PM square? We have PM out here and we have PM out here, so we do not require. So we write it again, MQ over MP equal to MP over MR. Cross multiply, MQ MR equal to MP into MP. So MQ into MR equal to MP square, and that's exactly what they're asking you. MP square can be written as PM square equal to QM into MR, and we have proved. Here, however, you just cannot write theorem 6.7. you got to write the entire words or the statement of theorem 6.7, which is on page 145 of your textbook. In the figure 6.53, ABD is a triangle right angled at A. So I'm just going to mark the right angle here. And AC perpendicular to BD. So here's another 90 when we have the same situation. So I quickly just mark earlier. So we have this must be equal here. That was wrong. It was A equal to D. And on the other side we have this was equal to B. And these were 90. And I need to prove AB square, BC and BD. Now AB square, so if you look up, I have to take the small triangle with the larger one. I need to take this triangle which will give me AB with the larger triangle. So we take in triangle ABC and triangle, the big triangle, that is ABD, and we show that they are similar, but we need to write the correspondence correctly to get our sum. So first we find which is the 90. In the smaller triangle C is 90, and in the larger triangle your A is 90. Then which is common? If you see here, B is common for both. So I write B here and there will be B here. Now which is the third angle left? The third angle left, we have CB will be A. We have seen here A. This A is equal to always D here. So I write A and D. Now we write the correspondence. Therefore, triangle CBA is similar to triangle ABD. And this is by theorem again 6.7. You have to write the statement of your theorem. Now, so we have CBA similar to triangle ABD. Now we write the side. So CB over AB will be equal to BA over BD, and then will be equal to CA over AD. We did AB square. Here's AB square. Now who gives us AB square? Where is AB square? AB square is in this ratio and in this ratio. So we do not need this one. We cancel that out. So now we continue. CB over AB equal to BA over BD. When I cross multiply, I get CB. I cross multiply these two, BD equal to AB into AB. So for CB I can write BC. BD equal to AB square, and I have proved. This is the same figure. Now we have to show AC square equal to DC and BC. So we have to take AC square twice, AC, AC. So in this case we're going to take the two small triangles. So we take up the small triangles, that is ACD and a triangle ACB. If we want this result, we must write our correspondence correctly. And in this case, we already have seen that this A will be equal to D. And here, this is our correspondence. And then we have 90 here. And there is 90 here. So let us start. So if I write angle C, I have to write C here because both are 90. Then for the lower triangle, if I write A on one side, I have to write D on the other side because they are equal. And then if I write B here, I have to write A here. So this I may just interchange. Here was ACD. I've taken the ACD on this side and the triangle ABC on this side. Now my correspondence I have got. So I have CAB, here CAB, similar to CDA. Now to write the sides, CA over CD equal to AB over DA equal to CB over CA. Now remember we require AC square, so look out for AC. There is AC out here and there is AC out here, so I don't need this. So I do now CA over CD equal to CB over CA. If I cross, CA equal to CB into CD. So I'll just continue here. So CA square equal to CB into CD. CA square can be written as AC square, CB as BC, and CD as DC, and I have proved. Here for the next sum, let me write in the beginning mark equal 90, and this is 90. Now let us see which triangles to consider. Do I consider the two small ones or the small and the big one? Here I require AD square, so I require AD twice. So definitely I've got to consider the small and the large triangle. So here I take the small one, and the small triangle is ADC and the larger triangle ABD. And I have to prove that they are similar. First, always take the 90. In the smaller triangle here, C is 90, and the bigger triangle A is 90. So I write A in the bigger triangle. So I'm writing it in the wrong place. I need to write A here. The big triangle, this is the big triangle A, and C of the small triangle. Now see which is common for both the triangles, and we see that D is common for both the triangles, the small and the large. So it is D and D, which is the third angle left now. In the smaller triangle, here I have A must be equal now to B. So the smaller triangle is A is a smaller triangle, B is of the larger triangle. So we have CDA is similar to triangle ADB, and this again theorem 6.7. Now for the sides, CD over AD is equal to DA over DB, which is equal to CA over AD. Now we require AD square. Now where is AD square? AD is here and AD is here, so I don't require this. So I write it again. CD over AD equal to DA over DB. Now we cross multiply, so we have CD into DB equal to DA into AD. So my CD, DB I can write as BD, and this is DA into DA with DA square, and I have proved. ABC is an isosceles triangle, a right angle at C. So here is my right angle. So this must be A, B and C. So this is my 90 degrees. So given triangle ABC, and in this triangle ABC, angle C is 90 and is given its isosceles. Isosceles means two sides should be equal. So I will take AC equal to BC, and I'll write AC equal to BC. And we need to prove AB square equal to twice AC square. So we start the proof. So by Pythagoras, we know it is a right angle triangle. So we can use Pythagoras theorem. Angle C is 90. Therefore, who is the hypotenuse? AB is a hypotenuse. So AB square equal to AC square plus BC square. So AB square equal to, now I know AC equal to BC. So I write here AC, and for BC again I write AC. And the reason, AC equal to BC, and this is given to us. So AB square equal to twice AC square, and I have proved it. ABC is an isosceles triangle in which AC equal to BC. If AB square equal to twice AC square, prove that ABC is a right triangle. Now I have to prove it is a right triangle. So what I do is I draw a right triangle right in the beginning. So I write given triangle ABC. I don't know it's a right triangle. I need to prove it. In this I have AC equal to BC, and also given to me AB square equal to twice AC square. I need to prove that ABC is a right triangle. Now I need to prove it's a right triangle. That means I'm using Converse of Pythagoras here. So let's start with the proof. So in triangle ABC, this is given AB square equal to twice AC square, given to me, which means AB square equal to AC square plus AC square. Twice AC square means AC square plus AC square. So AB square equal to, this is AC square, but I know AC square is equal to BC is given. So here I will write BC square. Reason, AC equal to BC is given to me. Now this looks something like converse of Pythagoras. So by converse of Pythagoras, I can say that AB is a hypotenuse. So by converse of Pythagoras, I can say a triangle ABC is a right triangle. And I know AB has to be the hypotenuse, because this is AB square here. So here is my hypotenuse. And if AB is my hypotenuse, angle C must be 90. So with AB hypotenuse, and therefore angle C equal to 90. ABC is an equilateral triangle of side 2A. Find each of its altitudes. So here we have triangle ABC is equilateral. Equilateral means all sides are equal. Which side? See, the side AB equal to AC equal to BC equal to 2A. We have to find its altitude. So we need to do a construction here. We do this construction AD, do it a little darker, AD perpendicular to BC. So construction, where AD is perpendicular to BC. Since AD is now the altitude, I can write therefore BD equal to DC. And this is property of equilateral triangle. The altitude bisects the opposite sides. Now BD equal to DC. Here we have BD equal to DC. So D becomes a midpoint. Here, this is the midpoint. Now, which will be equal to half of BC. So BD is equal to half of BC, and BC we know is 2A. So BD equal to A. Let me mark that in the figure. So I have BD here, which is now equal to A. Then we have AB, which is already taken as 2A, and I need to find AD. Here is 90 degrees, so I can use Pythagoras theorem. So in triangle ABD, angle ADB equal to 90. So the Pythagoras theorem, which means AB square equal to BD square plus AD square, reasoned by Pythagoras theorem. I'll be sending the PDF of this exercise, so you need to write the statements according to the PDF. Here I'm doing it in short. So AB is 2A the whole square, BD A square, and this AD square I need to find out. So 2A became 4A square equal to A square plus AD square. So when I take the A square on the side, becomes 3A square. 3A square equal to AD square. So let me do it here. So AD is under root of 3A square. So AD is A under root 3. So I get this is A under root 3. Prove that the sum of the squares of the sides of a rhombus is equal to the sum of the squares of the diagonals. So here we are given A, B, C, D is a rhombus, and they said show that the sum of the squares of the sides would be, we need to prove this. The sides are AB, so AB square plus 4 sides, BC square plus DC square plus AD square equal to sum of the squares of the diagonals. Diagonals are AC square and BD square. This is what we need to prove. But before we start this, let us use some properties of the rhombus. One property of the rhombus is the diagonals bisect, which means AO equal to OC. So I write that AO equal to OC. and also OD equal to OB. And for both this, the reason is the same, that the diagonals in rhombus bisect. Another property is they always bisect at 90 degrees. So here I can write angle DOC equal to 90 because the diagonals in the rhombus bisect at 90. Now we'll use Pythagoras theorem in our right angle triangle. Now which is a right angle triangle? We're going to take, there are 4 right angle triangles, but I'm going to take this one. So in triangle DOC, we know angle DOC is 90. We've already shown that. So the hypotenuse is DC. So DC square equal to DO square plus OC square. And this is by Pythagoras theorem. Now for the next DC square. Now DO is half of DB. So for DO, I'll write DB over 2 the whole square. And OC, if you look at OC here, this is OC. And OC is half of the diagonal. So for OC, I will write AC by 2 the whole square. The reason for this is statement 1 and statement 2, because so we write by 1 and 2. We can also write this. We know DB in OD is half of DB and OC is half of AC. Now we continue. So we have now DC square equal to DB square over 4 plus AC square over 4. So here is where we left. Now let's take LCM. 4 is the LCM. So I have DB square plus AC square. Take the 4 on the other side. So I get 4 DC square equal to DB square plus AC square. Now here I have 4 DC square, which means I have DC square plus DC square 4 times DB square plus AC square. Now all the sides of a rhombus are equal. So AB equal, all these 4 sides are equal. So for DC, I will write DC. But for the other sides, like for DC square here, I can write AB square because DC equal to AB. For DC, I can also write BC square because DC equal to AB. All 4 sides are equal. And for DC square, I can also write AD square because all the 4 sides of rhombus are equal. So DB square plus AC square. So I get DC square plus AB square plus BC square plus AD square equal to DB square AC square. And I have proved that the sum of the squares of the sides equal to sum of the squares of diagonal. And we did this by Pythagoras theorem. The 4 sides, the sum of the 4 sides square equal to sum of the squares of these 2 diagonals. And the property we used here was Pythagoras theorem in this triangle. And we did DC square equal to OC square plus OB square. And then for OC, we wrote half of AC, the entire AC. And for OD, we wrote half of dB.